For almost 200 years, astronomers had a question they couldn't answer. Why is the night sky dark? If the universe contains trillions of galaxies, and it does, and each of those galaxies contains hundreds of billions of stars, and they do, then every line of sight from your eye out into space should eventually hit a star. The entire sky should glow. Day and night should be identical. There should be no darkness anywhere. And yet, every night, darkness returns. It took until the 20th century to solve that puzzle. Scientists found 3 reasons. The universe has a beginning, so light from the most distant places hasn't reached us yet. Space is expanding, which stretches the light until our eyes can't detect it. And most galaxies are simply too faint to see without a telescope. 3 reasons. Clean, complete, settled. That was the answer. Then, in January 2026, a telescope confirmed something that should have been impossible. A galaxy called MOM-Z14, existing just 280 million years after the Big Bang, less than 2% of the universe's current age, and 100 times brighter than any theory predicted it should be at that age. Not twice as bright, not 10 times. 100 times brighter than the models said was physically possible. And it was not alone. Webb had been finding these overachievers for 4 years. The early universe appears to have contained roughly 100 times more bright galaxies than every theoretical model predicted before the telescope launched. The 3-part answer to the dark sky question still works. The sky is dark for the reasons scientists found, but the picture of what is out there, how many galaxies, how bright, how early, how structured, is wrong in ways nobody fully understands yet. The question, why is the sky dark, has been answered. The follow-up question, what exactly is hiding in that darkness, has just gotten dramatically more interesting. Let me show you both. The puzzle has a name, Olbers' paradox, after the German astronomer Heinrich Wilhelm Olbers, who formalized it in 1823. But the question is older. Edmund Halley, yes, the comet, raised it in 1720. Edgar Allan Poe, the horror writer, actually published a remarkably close solution in a prose poem in 1848. For 2 centuries, the brightest minds in astronomy circled it without landing cleanly. The logic that makes it inescapable goes like this. Assume the universe is infinite. Assume stars are spread through it in roughly uniform density. Now imagine standing at the center of a sphere and asking, how much starlight reaches me from all the stars within this sphere? The farther out you go, each shell of space contains more stars. The volume of a shell grows with the square of the radius, but the brightness of each individual star falls off with the square of the distance. The 2 effects cancel exactly. Every shell of space contributes the same total brightness, regardless of how far out it sits. And if there are infinitely many shells, stretching to infinity in every direction, the total brightness they contribute is infinite, not bright, infinite. The night sky, under a simple infinite static universe, should not just glow, it should be so bright it would kill you. The obvious escape routes don't work. Maybe dust blocks the distant light? No. Dust absorbs energy and re-radiates it. Given enough time, the dust heats to the temperature of starlight and starts glowing itself. You can't hide infinite light behind finite dust. Maybe the light is just too dim to see? No. We're not asking about visibility with human eyes. We're asking about the total energy flux. Even in infrared, in radio, in X-rays. If the universe is infinite, old, and uniform, the sky should be uniformly, murderously bright in every wavelength simultaneously. The puzzle stood for 200 years because every simple solution broke under scrutiny. The real solution required a completely different understanding of what the universe is. The answer required 2 of the most disorienting discoveries in the history of science. The first, the universe had a beginning. In 1929, Edwin Hubble published his observation that every distant galaxy is moving away from us. And the farther away it is, the faster it recedes. The universe is not static. It is expanding. And if it is expanding now, it was smaller in the past. Run the expansion backward, and you arrive at a single point, the Big Bang, approximately 13.8 billion years ago. That finite age is the first reason the sky is dark. Light travels at a fixed speed, 186,000 miles per second in a vacuum. In 13.8 billion years, light can only travel 13.8 billion light years. Beyond that distance, space exists, but the light from it hasn't arrived yet. We are surrounded by an information horizon, a sphere of observable space beyond which the universe is real, but dark to us. Not because there's nothing there, but because the signal is still in transit. The second discovery: space itself is expanding, and that expansion stretches the light traveling through it. When a galaxy a billion light-years away emits a photon of blue light, that photon spends a billion years traveling through expanding space. As space stretches, the photon's wavelength stretches with it. By the time it reaches us, it has shifted from blue to red. Push it far enough, and it shifts from visible red to infrared. Push it to the most distant galaxies, and it shifts into the microwave range, completely invisible to human eyes, detectable only with specialized instruments. This is redshift. It is one of the most confirmed phenomena in all of physics, measured across hundreds of thousands of galaxies. It means the light is real and still arriving. We just can't see it without the right tools. Together, these two facts, finite age and redshift, solve most of Olber's paradox. The universe is not infinite in time, and the light from its most distant regions has been stretched into invisibility. The third factor is the one that connects to where things get really strange. Most galaxies are simply too faint, too small, or too far away for us to see. Our best telescopes can only resolve so much. The observable universe, the sphere of space from which light has had time to reach us, contains roughly 2 trillion galaxies by current estimates. But we can directly image only a fraction of them. The rest exist in a darkness that is not empty, but merely beyond our current reach. That three-part answer, finite age, redshift, instrumental limit, explains why the night sky is dark. What it does not explain is what Webb found when it actually looked. The James Webb Space Telescope launched on Christmas Day, 2021. It is designed specifically to observe the universe in infrared, the exact wavelength range that contains the redshifted light from the most distant, earliest galaxies. Where Hubble was largely blind to the early universe, Webb can see it. The telescope's primary mirror spans 6.5 meters, 18 gold-coated hexagonal segments of beryllium, and collects more than 6 times as much light as Hubble's 2.4-meter mirror. It sits 1.5 million kilometers from Earth, beyond the Moon, protected from the sun's heat by a 5-layer sunshield the size of a tennis court that provides the equivalent of SPF 1 million sunblock. Its operating temperature is about minus 233 degrees Celsius, necessary because the infrared detectors have to be colder than almost anything in the solar system to function. By April 2026, it had completed nearly 4 years of science operations. The results have been, to use the measured language of the astronomers involved, unexpected. Standard cosmological models, the Lambda CDM model, the framework that has governed our understanding of how the universe evolved since the 1990s, make specific predictions about what the early universe should look like. At 300 million years after the Big Bang, you should see small, faint, diffuse protogalaxies. Primitive structures still assembling from the raw hydrogen and helium of the Big Bang. Stars just beginning their first generations. Heavy elements like carbon and oxygen, which require multiple generations of stellar life and death to produce, should be essentially absent. That is what the model said. What Webb found instead were galaxies that are massive, structured, and chemically enriched at epochs where none of that should have been possible yet. In January 2026, astronomers published confirmation of MOM-Z14, a galaxy at redshift 14.44, placing it just 280 million years after the Big Bang. Its light has been traveling for approximately 13.5 billion years to reach us, and it is not a faint, diffuse smudge. It is bright, compact, and shows spectroscopic signatures of nitrogen, a heavy element that requires multiple generations of stellar evolution to produce. Multiple generations of stars, born and died, in the first 280 million years of a universe that was supposed to be just getting started. The lead researcher, Rohan Naidu of MIT's Kavli Institute, said, "With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted." MOM-Z14 broke its own record. The previous most distant confirmed galaxy, JADES-GS-Z14-0, had a redshift of 14.18, placing it at 290 million years after the Big Bang. MOM-Z14 is at 14.44, 280 million years. Webb broke its own record, confirming a galaxy closer to the Big Bang than any previously confirmed. And it is not alone. It is one of a population. The research team estimates that the early universe contains approximately 100 times more bright, compact galaxies than any model predicted before Webb launched. Not twice as many, not 10 times, 100 times more. As MIT postdoctoral researcher Jacob Shen put it, there is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. Growing chasm is a phrase that, in the careful language of academic science, means we don't know what is going on. Let me be precise about why these galaxies are theoretically difficult, because the phrase challenging current models gets used so often in science journalism that it has lost most of its weight. Forming a massive, structured galaxy with heavy elements requires a specific sequence of events. Gas must collapse under gravity to form the first stars, population 3 stars, made almost entirely of hydrogen and helium, the only elements the Big Bang produced directly. Those stars burn hot and fast and die in supernovae, forging heavier elements in their cores and scattering them into surrounding space. That material then recondenses, forms a second generation of stars with heavier chemical compositions, which live and die in turn, enriching the gas further. This process, repeated across multiple stellar generations, is what produces a galaxy with the chemical profile Webb is detecting in objects like MOM-Z14. The problem is time. In the Standard Model, the first stars ignite perhaps 100 to 200 million years after the Big Bang. For multiple generations of stellar evolution to then unfold, for the gas to cycle through stars multiple times, each time enriching it with heavier elements, requires hundreds of millions of years of additional time, at a minimum, under conservative assumptions about how quickly stars form, live, and die. MOM-Z14 exists 280 million years after the Big Bang. That is barely enough time, under standard assumptions, for the first generation of stars to form. And yet it shows nitrogen, an element that requires not one, but multiple generations of stellar processing to appear in significant quantities. Several competing explanations are currently being debated, and none is universally accepted. Explanation 1. Star formation in the early universe was dramatically more efficient than current models assume. Under the intense conditions of the early cosmos, higher gas densities, different temperature profiles, possibly different dark matter interactions, stars may have formed and died at rates that compress what normally takes billions of years into hundreds of millions. If star formation rates were 10 or 50 times higher than today's models predict, the timeline problem largely dissolves. Explanation 2. The role of dark matter in early structure formation is different from what the Standard Model assumes. Dark matter makes up roughly 27% of the universe's total energy content and is the gravitational scaffolding around which ordinary matter assembles into galaxies. But we do not know its detailed properties at the particle level. If dark matter interacts differently in the early universe, perhaps through self-interactions or unusual decay channels, it could have accelerated the formation of the dense halos inside which galaxies assemble. Some models involving warm dark matter or fuzzy dark matter predict different early structure formation than the standard cold dark matter picture. Explanation 3. The most unsettling option. Something is wrong with the cosmological timeline itself. Not catastrophically wrong. The Big Bang, the expansion of space, dark energy, and cosmic microwave background are all confirmed by multiple independent lines of evidence. But the precise value of cosmological constants, like the Hubble parameter, which sets the rate of expansion, and therefore the age and size of the observable universe, has been in dispute for several years. The Hubble tension, as astronomers call it, is a disagreement between two different methods of measuring the expansion rate, yielding results that differ by enough to be statistically significant. If the Hubble constant is even slightly different from its current best estimate, the universe's age and the distances to early galaxies shift correspondingly. None of these explanations has been ruled out. None has been definitively confirmed. What astronomers agree on is that the data from Webb is real. It is consistent across multiple observing programs and independent teams, and it cannot be explained by calibration errors or instrument artifacts. The galaxies are there. The models do not fully account for them. The early galaxy problem is the most theoretically significant finding, but Webb's 4 years of observations have reshaped our picture of the universe across multiple areas simultaneously. The epoch of reionization is the period, roughly 400 million to 1 billion years after the Big Bang, when the universe transitioned from a foggy state, neutral hydrogen gas filling all of space, blocking most light, to the transparent state it is in today. Something ionized that hydrogen. Something stripped the electrons from it and cleared the cosmic fog. For decades, astronomers debated what? Quasars? Large galaxies? Some combination? Webb's Uncover survey answered this question in 2025 with direct observational evidence. The agent of reionization was not large, bright galaxies. It was small ones, tiny, faint, low-mass galaxies bursting with newborn stars, so numerous and so energetic that their combined ultraviolet output was sufficient to ionize the universe's entire hydrogen content. The study, published in 2025, found 83 such galaxies and concluded their combined output could account for all the ultraviolet light needed to clear the cosmic fog. The universe was remade not by giants, but by an overwhelming multitude of dwarfs. In February 2026, astronomers from the University of Pittsburgh published confirmation of a barred spiral galaxy, a fully mature, structured galaxy of the type our own Milky Way belongs to, at a distance corresponding to just over 1 billion years after the Big Bang. Barred spirals require billions of years of evolution under standard models to develop their characteristic structure. Finding one this early forces revisions to models of how quickly galaxies settle into their mature morphologies. Also, in January 2026, researchers from Texas A&M reported the discovery of a 5-galaxy merger event occurring 800 million years after the Big Bang, galaxies colliding and combining far earlier than predicted, redistributing heavy elements across distances larger than any model had anticipated at that epoch. And separately, Webb identified several hundred mysterious objects it cannot yet classify. Dubbed little red dots by astronomers, these compact, red, extremely luminous objects may be a previously unknown category of celestial object, possibly black hole stars, hybrid structures that should not be stable under any known physics. Their nature remains genuinely unsettled. 4 years of observations. Epoch of reionization solved. Early galaxy formation broken. Morphological timelines pushed earlier. Galaxy mergers happening sooner. And a new category of object with no confirmed explanation. The dark sky is dark for the reasons we thought. What is hiding in it is stranger than any previous version of the theory described. Webb is not the last word. The Nancy Grace Roman Space Telescope, NASA's next flagship space observatory, targeted for launch as early as late 2026, is designed to complement Webb in a specific and important way. Webb is extraordinarily sensitive, but has a relatively small field of view. Each observation covers a tiny patch of sky. Accumulating the statistical samples needed to understand the early galaxy population, thousands of confirmed high redshift galaxies, rather than dozens, requires either decades of Webb observing time or a different instrument. Roman's primary mirror is the same size as Hubble's, 2.4 meters, smaller than Webb's 6.5 meters. But its field of view is 100 times wider. It can survey the sky at the same resolution as Hubble, but across an area 100 times larger per observation. The research team behind MOM-Z14 specifically anticipated Roman's contribution in their published paper, writing that the telescope will boost the sample of bright, compact, chemically enriched early galaxies into the thousands. Thousands of confirmed objects at extreme redshifts, rather than dozens, would allow astronomers to map the statistical distribution of early galaxy properties and definitively test which of the competing theoretical explanations, efficient star formation, modified dark matter, revised cosmological constants, actually fits the data. Beyond Roman, the ground-based Extremely Large Telescope, a 39-meter optical telescope under construction in Chile, will provide spectroscopic follow-up capability that neither Webb nor Roman can match, allowing detailed chemical analysis of early universe objects at angular resolution Webb cannot achieve. The tools are being built. The questions are specific and testable. The anomalous bright early galaxies are real and documented. This is not a crisis of the kind that overturns the Big Bang model or the expansion of space. Those are confirmed by entirely independent lines of evidence that would not shift even if every early galaxy theory proved wrong. What is shifting is the detailed picture of how matter organized itself in the universe's first few 100 million years. And that picture, it turns out, organized itself much faster, much more efficiently, and into much more complex structures than anyone expected. The question is simple. Why is the night sky dark? The answer is three things. The universe had a beginning 13.8 billion years ago, so light from beyond that horizon hasn't arrived. The expansion of space has stretched the light from distant galaxies into infrared and microwaves, invisible to human eyes. And most of the 2 trillion galaxies in the observable universe are too faint, too far, or too small for current telescopes to resolve. That answer is complete and correct. It was established across decades of careful observation and confirmed by multiple independent methods. And while we were confirming it, we built a telescope to look at what was actually out there in the darkness. And the thing looking back was not what the theory predicted. Galaxies that should have taken billions of years to form, assembled in hundreds of millions. Structures that required multiple generations of stellar evolution, appearing before the first generation should have finished. 100 times more bright objects in the early universe than every model said was possible. A category of object, the little red dots, that doesn't fit any known classification. A growing chasm, in the words of the researchers who found them, between theory and observation. The darkness is explained. What is hidden inside it is not. MOM-Z14 sent its light toward us 13.5 billion years ago, 280 million years into a universe that had just begun. It has been traveling ever since, through the expanding, cooling, galaxy-filled space between its origin and this planet, arriving at a telescope we launched 4 years ago and pointed at the right patch of sky at the right moment. The sky is dark because the universe is young enough that most of its light hasn't arrived yet. But the light that has arrived is telling us that something happened in the universe's first moments that we do not yet understand. The next time you look at a dark sky, you are not looking at emptiness. You are looking at the light travel limit of a 13.8 billion-year-old universe, a sphere of information beyond which reality continues, but the signal hasn't reached you. And inside that sphere, there are 2 trillion galaxies, most of them invisible, and the ones we can see, don't fully match the theory we built to explain them. The darkest parts of the sky are the parts where the most urgent questions live.